All right, so on homework 39, we are simplifying radical expressions. Most of the time we'll be doing square roots, but when we simplify these, we could either simplify underneath first and then multiply, or we can just go ahead and multiply, which is what we're going to do because our numbers aren't very big. If your numbers were like 216 or something like that, I'd probably simplify it first, but since it's a 2 and a 6, I can multiply those pretty easy. So I'm going to go ahead, multiply what's under the square roots together. So 2 times 6 is 12. X squared times an x, I add my exponents, so x to the third. U to the fourth times a u squared, u to the 6th power. So now I want to simplify what I have there like we did on Monday's page. I'm going to look at this and say, okay, 12 is not a perfect square. If it were a perfect square, I'd leave it alone. It's not, so I want to try to factor it. Factors of 12, one of which is a perfect square. Probably want to use 4 times 3. My exponents, if it's an odd exponent, I want to factor out one of them. So x to the third, I factor into x squared times x. U to the 6th has an even exponent, which means it is a perfect square, so I leave that alone, just like we did the other day. And then I'm going to go ahead and take out my perfect squares. So square root of 4 is 2. Square root of x to the 2nd would be x to the 1st, because I take half of my exponent. Square root of u to the 6th is u to the 3rd. Again, taking half of my exponent. And I have the 3 and the x left underneath my square root. And so I get 2xu cubed square root of 3x. So basically all you're going to do is multiply them together and then simplify them like we did the other day. So number 2, if we multiply that together, what would we have under our square root?
36y to the 10, w to the 10.
And I look at that and I say, okay, 36 is a perfect square, I'm going to leave that alone. Y to the 10th is a perfect square because it has an even exponent, I'm going to leave that alone. And w to the 10th is also a perfect square, I'm going to leave that alone. I don't need to factor anything out because all of my values there are perfect squares and I can just take my square roots. Square root of 36 is 6, square root of y to the 10th, y to the 5th, and square root of w to the 10th, w to the 5th. And I have nothing left under the square root since everything was perfect squares. My radical sign is gone. I just get 6y to the 5th and w to the 5th. Number 3 then, when I go ahead and multiply that one, I would get
36, 36x to the 6th, u to the 7th.
U to the 7th. So looking at that one, the 36 is a perfect square, the x to the 6th is a perfect square, but the u to the 7th is not. What would we want to do with the u to the 7th?
Break it down to u to the 6 times u.
Break it down into u to the 6 times u. Take out one of my variables. So now if I take out my perfect squares, I can take out
36.
square root of 36 is 6.
X to the 3rd.
X to the 3rd.
U to the 3rd.
U to the 3rd. And left under the radical, square root of u. So 6x to the 3rd, u to the 3rd, square root of u would be my answer. The next ones, they are working with fractions that are under the square root. And basically, the same thing holds true. Since the whole thing is under the square root, I could think of that as one big problem under the square root. So I would have y to the 10th, z to the 9th over 2 times 8x to the 7th over x to the 5th, y to the 6th, z to the 9th, like it was under one big square root and instead of 2 separate ones. Well, when I'm multiplying fractions, I can go ahead and do some reducing. So I can say, oh, 2 goes into here once and into here 4 times. I've got a y to the 10th and a y to the 6th, so I can take out 6 of them, which leaves me y to the 4th. I've got a z to the 9th and a z to the 9th. Those are just going to cancel each other out. And I've got an x to the 7th and an x to the 5th. If I take out 5 of them, I get an x squared. So under my square root, I'm going to have 4y to the 4th and x squared. There's nothing left on the bottom because everything canceled out there. Now I can simplify that. Again, in this case, all of those things are perfect squares, so I can just go ahead and take my square root. The square root of 4 is 2. Square root of y to the 4th is y squared. And the square root of x squared is x. And if you had 2xy squared, it'd probably be even better, but it really doesn't matter which order you have your variables in. So I probably really didn't need to rewrite that as one big square root. Again, they want to get across on the next one here that even though these are two separate square roots, I could write it as one big square root and put it all together. So since everything's under square roots, I would treat it just like the whole thing was under one big square root and go ahead and do my reducing. So what can I do with number 5?
Three goes into 27 9 times.
3 goes into 27 9 times.
W goes into 6. 4.
I'm going
Or
to take
W
out 4.
And there's 2 left.
And there's 2 left over, exactly.
And then there's going to be 6 left over on the top.
I'm going to take off 7
Y.
y's, and I'm going to get y to the 6th on top.
And then Z is just completely.
Z's cancel out altogether. So those are still under the square root. We have 9w squared and y to the 6th, all under my square root. And again, all of those happen to be perfect squares, so I can take the square root of all of those, and I would get
3WY to the 3rd.
3wy to the 3rd. And number 6 is going to be the same kind of thing. So if I reduce that one down, what can I do with that one?
9 goes into 81 9 times.
9 goes into 81 9 times.
W to the 3rd and W to the 5th. There's going to be 2 left over on top.
So I get w squared on top.
There's going to be Y in the 2nd on top. And then Z's cancel out.
Z to the 8ths cancel out. So I have the square root of 9w squared y squared, which again are all perfect squares. So if I take my square root, my answer would be
9WY.
not 9wy, 3wy. That's what you meant.
Yeah, that's what I meant.
3wy. So not too bad, right? The next ones are going to talk about rationalizing the denominator of my radical expression. When they tell you to rationalize the denominator, what they're really telling you is to get the square root out of the bottom of the fraction. In best form, you never want to have the square root in the denominator. And so there's a few things you can do. One thing is you could just multiply by itself, but if you have a big number there, you probably don't want to have to take the square root of 35 times the square root of 35 because it's going to be really huge. So you can look at it to see if they're both under square roots, can I reduce it? Now if one's not under the square root and the other one is, I can't reduce it. But if they're both under square roots, like on the previous problem, I can reduce. So in this case, I can divide both of these by 7 and make that the square root of 3 over the square root of 5. And now my numbers aren't so big. Now I'm going to rationalize the denominator by multiplying by what's in the denominator. And of course, I'm making an equivalent fraction, so technically I'm multiplying both the top and the bottom by whatever's in the bottom. On the top then, I'm going to have the square root of 15. On the bottom, I'm going to have the square root of 25, which should be a perfect square because I took 5 times 5, right? I can then simplify the bottom, and I'm going to have the square root of 15 over just a plain old 5. Again, I would want to think about, can I simplify the square root of 15? In this case, I can't because 15 doesn't have any factors that are perfect squares other than 1. And so if you would have something like 32, then those were the ones we were simplifying the other day, and we try to simplify it farther. But in this case, I can't. And again, I can't reduce that down because one's under the square root and the other one is not, so I can't do any reducing with that. Number 8, I want to rationalize the denominator and simplify. In this case, I have the square root of 6 over the square root of 11. I can't do any reducing, so I just want to rationalize the denominator by doing what?
Taking them both by the square root of 11.
Taking them both times the square root of 11. So I'm going to get the square root of 66 over the square root of 121. And square root of 121 should now be a perfect square. The square root of 121 is 11, right? We took 11 times 11 to get 121, so the square root of 121 is just an 11. No longer has the square root sign over the top of it, so it's rationalized. Again, you would think of 66 to see, can I simplify the square root of 66? But I would have like 2 and 33, none of those are perfect squares. 6 and 11, those aren't perfect squares. So there aren't any factors that I can factor that into so I could simplify that any further. And number 9, same kind of thing there. I want to rationalize the denominator. So even if I could have reduced these, I can't because one's not under the square root and the other one is. So I'm just going to go ahead and rationalize my denominator by doing what?
Timesing it by 2?
Timesing it by the square root
Oh, yes.
of 2. Square root of 2. And in this case, when I take 11 times the square root of 2, one is not under the square root and the other one is. It's like when you take an 11 times an x, you just put the number in front of the square root. So you write it as 11 square root of 2. That means 11 times the square root of 2. On the bottom, you're going to get the square root of 4, but you can simplify the square root of 4 into 2. So I'm going to get 11 square root of 2 over 2. Now in this case, if I could do these two numbers without the square roots and reduce them, I could do that. But I can't take 11 divided by 2 and reduce it at all. So that is in simplified form. If it was 10, I could reduce, but in this case I can't. So either if they're both under the square root you can reduce, or if they're both not under the square root you can reduce. (10, 11, and 12), we're still rationalizing the denominator. They still want you to know that, oh, if it's under one big square root, I could put them both under a square root and say, oh, this is the same thing as the square root of 2 over square root of 3. Again, we can't reduce that down, so we want to rationalize the denominator by doing what?
Multiplying it by square root of 3.
Taking it times the square root of 3. And if I do that, I'm going to get
Square root of 6 over square root of 9.
square root of 6 over square root of 9. And then taking the square root of 9, I would get an answer of square root of 6 over 3. And again, I can't reduce that because one's under a square root and the other one is not under the square root, which is the point of rationalizing the denominator. Oops, number 11. So I want to rationalize the denominator and simplify on that one. Looking at that one, what might I want to do first?
Put both under square root.
I could do that. I could make that the square root of 3 over the square root of 21. Then what might I want to do with that?
Times them by 21.
I could do that, but I could make my problem a little bit easier.
Can we simplify?
Oh, I can simplify, right? 3 over 21, I can divide those both by 3. That's going to make my problem. But I could multiply by the square root of 21. I just have really big numbers to work with. So it's easier if I can reduce first. So if I reduce them down, what am I going to get?
1 over 7.
Square root of 1
Oh, yeah, square
over
root
the
of
square root of 7, right? Now what might I want to do with that? Multiply by the square root of 7. And if I multiply by the square root of 7, what would I get?
Square root of 7 over square root of 49.
Exactly. Square root of 7 over the square root of 49. And then simplifying that, I'm going to have square root of 7 over 7. And again, now my denominator is rationalized. I can't reduce because one's under a square root and the other one's not under a square root. Number 12, same thing, rationalizing my denominator. So what should I do with that one?
Put them both under square root.
Make that the square root of 7 over the square root of 3.
And then times by the square root of 3.
And times by the square root of 3. I would then have the square root of 21 over the square root of 9. Right, 21 over 9 is not the same thing as the square root of 21 over the square root of 9, because now I got to do my square roots, or the only one I can do. So my answer is going to be
Square root of 21 over 3.
square root of 21 over 3. Be careful when you're typing those in on Alex. I would hit the fraction button first, because if you don't, they're going to try to put the square root over the whole fraction, and it's going to look like this, which is not the same thing as that. So hit the fraction button first, then put the square root on top and the plain number on the bottom so that it goes in correctly. And you say, how come I got the wrong answer? I did it right. And then we are going to solve some radical equations that simplify to a linear equation with one radical sign. When I'm trying to simplify something with a radical sign, I first want to make sure that that radical sign is by itself. So if there's anything next to it, if it's a plus 5 way on the end or times 2, I need to get rid of that first. Once the radical is by itself, like on this first problem, I'm going to get rid of the square root by doing the opposite. What's the opposite of a square root?
Not a square root?
Not a square root. Well, you're right, it's not a square root. What do you think the opposite of taking the square root of something is? It is squaring something. If I have this, if I have the square root of 3 and I square it, that means I'm going to have the square root of 3 times the square root of 3, right? Because squaring means times itself. Square root of 3 times the square root of 3 is the square root of 9, which is now a perfect square, and the square root of 9 just gives me 3. So when you square a square root, it undoes it because they're inverse operations, and you just get what's underneath the radical sign. So that's what we're going to do to solve something with a radical. If I have the square root of w minus 11 equals 5, what I'm going to do is square both sides of my equation. Because if I do it to one side, I have to do it to the other side. When I square the square root, it's going to eliminate that and just give me the w minus 11 that's underneath there. The other side didn't have a square root. I have to square that. 5 squared?
25.
25. In order to solve that, what would I do?
Add the 11.
Add the 11. So w is going to equal 36. Now, when you're working with radical expressions, sometimes you get what's called an extraneous solution. You worked it out correctly, but when you check it, it doesn't check. So you always want to make sure you go back and check your answers to make sure that they work out properly. So I'm going to check my answer by putting 36 in here and saying, okay, 36 minus 11 is 25. The square root of 25 is 5. Yep, that one checks out. That's going to be a good answer. So number 14, if you look at that one, I'm solving it for you, but notice on this one, the square root part isn't by itself. So before I square both sides, I need to move my number over to the other side. Because otherwise, if I tried to square this, I would have to FOIL that out and I'd have a great big huge mess and it wouldn't be very fun. Well, it might be fun for me. So I'm going to go ahead and move my 2 to the other side first. So since it's a minus 2, I have to add my 2 and make this problem the square root of u minus 6 equals 7. Now it looks like that previous one. So what do I do with that?
Exponent of 2?
I'm going to square both sides. Yep.
Yeah, square both sides.
Square both sides. And if I square both sides, which am I going to get?
U minus 6 equals 49.
U minus 6 equals 49. And Kenyon, if I want to solve that, what would I do?
It is 6 to 4.
Add 6 to 49, exactly. Wasn't a trick question. U then is going to equal
55.
55. Again, I want to check that to make sure that's a good solution. So I would say, okay, 55 minus 6 is 49. The square root of 49 is 7. 7 minus 2 is 5. Yep, that's what I had over there. So that is a good solution. Number 15 then, if I want to solve for u, what should be my first step?
First you have to minus the 14.
First I have to minus the 14. So I would have the square root of u plus 20 equals negative 13. Then what would I do with that?
Square both sides.
I would square both sides. And if I square both sides, what am I going to get?
U plus 20 equals negative 169.
Now when you take a negative 13 times a negative 13, you get a
Positive.
positive 169. And then to solve that,
Minus the 20.
minus the 20. So u is going to equal 149. Now if I check that one, what happens here? If I put my 149 in there, 149 plus 20 is 169. The square root of 169 is
13.
13. 13 plus 14 is
27.
27. Does that equal 1? No. This is one of those where you have that extraneous solution because you squared this negative and it made it positive, and therefore it doesn't check. So watch for that, or make sure you're checking your answers. All right. Those are the next 5 things on your pipe chart. Questions on any of those? You're ready to go then.